This story begins long before people walked the Earth, even before the dinosaurs, before the first signs of life appeared on this planet, before anything existed at all. The Big Bang, the birth of our universe. From this new matter, the first galaxies took shape. Nebulae formed inside the galaxies, and inside the nebulae, the first stars were born. The sun was about to make its appearance in the same way, surrounded by a rotating disk of dust and gas. Gravity pulled the dust particles together, and they turned into huge masses that grew and attracted other masses, future planets. The gases gathered in the sun, which finally lit up. The planets grew thanks to large and small meteorites that rained down from the sky. The energy of each new impact was transformed into heat that gradually warmed up the young planets. Eventually, these became the worlds we know today: Jupiter, Saturn, Mars, and of course, Earth. But what happened to the heat that was accumulated while our planet was being formed? It's still there, hidden in the innermost layers of the Earth's core, and it's constantly reinforced by natural radioactivity. The heat is continually transmitted to other layers before being freed into space. During its journey toward the surface, the heat moves semi-fluid rocks it meets along the way. Like water boiling in a pot, the rocks in each layer rise upward and shed their heat. Then they fall and get heated again. Like huge and very slow cogs in a machine, their movements shift the plates or enormous sheets that make up the thin outer layer of the Earth's crust. In this way, they move whole continents. After 200 million years, this is the result. But the plates are interlocked. That's why, when they shift, the jerky movement along the edges that separate them causes what we call earthquakes. Most of the earthquakes recorded in the world aren't very strong, but sometimes a particularly great one causes destruction and death. Earthquakes also occur at the sea bottom. When that happens, they can sometimes displace the water column and originate waves. These waves are best known by their Japanese name, tsunami, which simply means harbor wave. Regular sea waves caused by the wind are very different from tsunami waves. Let's find out why. Wind blowing over the sea can only move the upper layer of water, forming waves but not affecting movements deeper down. The water particles near the surface move with a circular motion, which helps to propagate the wave along. Deep down, the water particles don't move. The strength with which these waves reach the coastline depends exclusively on the movement in the first few meters of water. A tsunami, on the other hand, can be generated at the bottom of the sea. In case of a strong earthquake, the sea floor abruptly deforms and vertically displaces the overlying water. The entire water column is disturbed by the uplift or subsidence of the sea floor. This sudden movement releases a great impulse of energy, which is transferred to the whole column of water between the surface and the sea floor.
Hey there, this is Brain Stuff, and I'm Josh Clark, and this is the Brain Stuff where I explain to you how tsunamis work. The word tsunami actually comes from two Japanese words, su, meaning harbor, and nami, meaning waves. Basically, when you put them together, it means that when these waves hit the harbor, brother, you better get out of there. There are some differences between a tsunami wave and a regular Joe Schmo wave, but any wave is actually an energy carrier. We tend to think of waves as water moving through itself, but actually, waves are energy moving through water. The difference between a tsunami wave and a regular wave is how that energy is transferred and how much energy that wave packs. So the ordinary typical Joe Schmo surfer dude wave propagates from wind blowing across the surface of the ocean. Well, Buckminster Fuller pointed out that the wind actually sucks, it doesn't blow, but that's a different Brain Stuff episode entirely. A tsunami wave, however, is propagated by some sort of underwater disturbance. These are called tsunamigenic events. So things like an underwater rock slide, or an underwater earthquake, or an underwater volcano can all set off a tsunami. So think of a rock pile or a couple of tectonic plates sliding against each other on a fault line as possessing a ton of stored energy. We call this potential energy. Now when one tectonic plate suddenly slips beneath the other, this potential energy is released as kinetic energy. This energy is transferred outward from the point of origin in much the same way as when you take a rock or a pebble and throw it into a pond. It creates ripples, right? Well, with a tsunami, these ripples, waves, radiate from the point of origin, traveling at hundreds of miles an hour, carrying with them a lot of energy. Now, if you're watching a tsunami wave out in the deep ocean, what you're going to see is about a 3-foot tall wave traveling really, really fast. But what you're seeing, metaphorically speaking, is just the tip of the iceberg. This incredibly deep ocean wave that's traveling so fast encounters, ultimately, the shoreline. The shoreline that slopes upward compresses the energy of the tsunami wave. It slows its velocity down tremendously, but it also forces it upward. So what was once a 3-foot wave is now something like 100 feet, and it's at the shore. One of the big misconceptions about tsunamis is that they exist as just one wave. But remember, they're a lot like a pebble created by a rock tossed into the pond. A bunch of ripples are created. When the first tsunami waves reach the shoreline and slow down, the waves in the rear start to catch up. They compress, forming what's known as a tsunami wave train. Since tsunamis pose such a danger, scientists are constantly trying to figure out how to deal with them. The thing is since we're talking about such a huge release of kinetic energy, once a tsunami starts, there's no stopping it. So the best science can hope for is to predict their path and power so they can warn coastal areas to clear out as soon as possible.
กูนำรถย่างเร็วเลยเลยแกมาคนเรือรถเล็กดูจังลำน้ำมันวนไปทางไหนมันเหมือนมีรูตรงนั้นน่ะนะต้องไปเปิดมาไม่เคยเห็นบอกแกที่ขึ้นเลยครับก่อนบอกพวกโรงแรมด้วยครับบอกกล้วยอย่างเล็ก
Die brechen da hinten und die Wellen, die brechen da hinten auch heftig, oder? Alter Schwede. Guck mal da hinten, Schnicki, wie das hochpasht, das Wasser.
ครับผมขึ้นมันจะใหญ่ขึ้นเรื่อยๆฮะ
Hammer. Was da hinten abgeht?
Irgendwie ein Seebeben gewesen sein. Das ist Wasser.
Nein. Aber da hinten, das ist ja Wahnsinn. Das ist richtig.
ผมรบกวนแจ้งแขกอย่างด่วนนะครับ ตอนนี้มีพายุ Run 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 go go
Wenn die Welle hier auf den Strand rauscht, ne?
Hier, die hauen noch alle ab, die Zeit.
quick quick เลยครับตอนนี้มาทะเลมากนะน้ำทะเลลดอย่างมากครับด่วนเลยครับ go go run run
Was ist das? Was ist das?
Tsunami.
Ja?
โอ้ยมาอย่างเร็วเลยนี่ไม่ยอมขึ้นนะไม่ยอมขึ้นวิ่งแล้ว
Komm, wir müssen los. Wir müssen weg. Nach hinten, komm. Wir müssen nach hinten.
Kom igen. Spring fort som fan. Spring.
I just happened to look over my shoulder. There were some people standing up. Other people had started to run.
Jag får riktigt jävla överkörning. Kom Sara.
I stood up, picked up my bag. In those few seconds of standing up, it had gone past my feet. It had taken my towel and ripped the headphones out of my ears. I heard just how loud the waves really were. So I started to run.
Ta in i hotellet. Sidan. Oj, jag vill. Nej,